Consider this. Pretty much every piece of plastic ever made is still somewhere on our planet. That is a truly staggering thought. From the toothbrush you used this morning to the packaging on your favorite snack, plastic is everywhere in our modern world. It is strong, it is cheap, and it is incredibly useful. But that usefulness comes with a very big price. Since we started making plastic in large amounts, humanity has produced over 8 billion tons of it. That is heavier than 1 billion elephants. A lot of that plastic has ended up where it should not be, in our oceans, our soil, and even inside our bodies. It is a global problem that grows bigger every single day. The core of the issue is that we make plastic much faster than we can get rid of it. Think about how easy it is to buy something wrapped in plastic and then throw that wrapper away. It takes just a few seconds, but that plastic wrapper can stick around for hundreds or even thousands of years. We're creating a mountain of waste that will outlive us all. This is not just messy, it is dangerous. Plastic pollution harms wildlife, disrupts ecosystems, and poses a growing threat to human health. We have gotten ourselves into a real pickle, a plastic pickle, and now we have to science our way out of it. So, what about recycling? We have been told for decades to reduce, reuse, recycle. It sounds like a simple, perfect solution. We put our plastic bottles and containers in a special bin, and they magically get turned into new things. If only it were that easy. The truth is, our current recycling systems are struggling to keep up. Globally, only about 15% of plastic waste is even collected for recycling, and a much smaller amount, maybe as low as 5% in places like the United States, actually gets turned back into new products. That means the vast majority of plastic is not being recycled at all. This recycling crisis is happening because it is often cheaper for companies to make brand new plastic from oil and gas than it is to use recycled materials. When oil prices are low, the economic incentive to recycle pretty much disappears. We are competing with a powerful, well-established industry that can produce new or virgin plastic at a very low cost. This makes it incredibly difficult for recycling facilities to turn a profit and stay in business. We are facing a mountain of plastic waste with a system that is not equipped to handle it. But don't lose hope. Science is on the case. Let's talk about why recycling plastic is so tricky. It is not like recycling glass or metal. With glass, you can melt down a green bottle and a brown bottle together, and you still get perfectly good glass. Plastic is different. There are many different types of plastic, and they do not like to mix. Think of it like trying to mix oil and water. They just do not combine well. If you melt different kinds of plastics together, you often end up with a weak, lumpy material that is not very useful for anything. This is a huge headache for recycling centers. To understand this better, look at the bottom of a plastic container. You will probably see a little number inside a triangle. That number, from 1 to 7, tells you what type of plastic it is. For example, number 1 is PET, which is used for clear soda and water bottles. Number 2 is HDPE, used for milk jugs. Number 5 is PP, used for things like yogurt cups. Each of these plastics has a different chemical makeup and melts at a different temperature. For recycling to work properly, you have to separate them all perfectly. This sorting process is expensive, time-consuming, and often has to be done by hand. Another big problem is contamination. Imagine you finish a jar of peanut butter and toss it straight into the recycling bin. That leftover peanut butter is a contaminant. So are paper labels, sticky glues, and leftover food or drink. When plastics are melted down, these contaminants can ruin the whole batch, lowering the quality of the final recycled material. Even a tiny amount of the wrong kind of plastic can cause big problems. For instance, PCB-verband or sprauben, posibacondil bevero derudants, physomaza deris, pomobrile lawbars, costibridan spalnic. Number 3, releases a harmful gas when heated that can damage expensive recycling equipment. It is like having one bad apple that can spoil the whole bunch. Because of all these challenges, the sorting, the mixing, and the contamination, most plastic that does get recycled is not truly recycled, it is downcycled. This means it is turned into a lower quality product. A clear water bottle, for example, might be downcycled into fibers for a carpet or stuffing for a winter coat. That sounds good, but that carpet or coat cannot be recycled again. Its next stop is almost always the landfill. We are not creating a closed loop where a bottle becomes a bottle again. We are just delaying the plastic's journey to the garbage dump. The most common way we have been trying to recycle plastic is called mechanical recycling. It is a pretty straightforward process. First, the collected plastic waste is sorted by type and color. Then, it is washed to remove as much contamination as possible, like dirt, food residue, and paper labels. After it is cleaned, the plastic is shredded into small flakes, melted down into pellets, and then those pellets can be used to manufacture new products. This is the system that has been in place for decades, and it is the one we are most familiar with. When it works, it is a great way to save energy and resources compared to making new plastic from scratch. However, mechanical recycling has some serious limitations, especially when it comes to quality. Every time you melt and reform plastic, its long chemical chains, called polymers, get a little bit shorter and weaker. It is like making a photocopy of a photocopy. Each new copy is a little fuzzier and less clear than the one before it. Because of this degradation, a piece of plastic can only be mechanically recycled a few times, maybe 2 or 3 at most, before its quality becomes too poor to be useful. This is why we cannot just keep recycling the same plastic forever using this method. This process works best for one specific type of plastic, PET, or number 1 plastic, which is what clear drink bottles are made of. It is relatively easy to sort and clean, so it has the highest recycling rate. But even for PET, the end product is often downcycled into things like polyester fabric for clothing. This fabric then sheds tiny plastic fibers, called microplastics, every time it is washed, which creates another form of pollution. For other types of plastic, like the films used for grocery bags or the mixed plastics in a yogurt cup, mechanical recycling is much harder and often not economically possible. So while mechanical recycling is an important part of the solution and works well for clean streams of certain plastics, it is not enough to solve the whole problem. It cannot handle the vast majority of plastic waste, which is often mixed, dirty, and made of complex materials. We are trying to fight a giant monster of a problem with a tool that is just not powerful enough for the job. To truly make a dent in our global plastic mountain, we need to look beyond the old ways and embrace new, innovative ideas. We need a science upgrade. Now for the cool new stuff. Imagine you have a big pile of mixed up Lego bricks, and you want to separate all the red ones from the blue ones. Doing it by hand would take forever. But what if you had a magic magnet that only pulled out the blue bricks? That is kind of what researchers at Northwestern University in the United States have developed for plastics. They have created a special chemical process that can sort different types of plastic on a molecular level, which is something we could never do before. It is a big step forward in tackling the problem of mixed plastic waste. This breakthrough focuses on a huge category of plastics called polyolefins. Things like polyethylene, used in plastic bags and milk jugs, and polypropylene, used in car parts and food containers. Together, they make up more than half of all the plastic we produce. The problem is that they are very hard to separate from each other. The new method uses a special ingredient called a catalyst, which is a substance that speeds up a chemical reaction. This particular catalyst, made from the inexpensive metal nickel, acts like a smart pair of scissors. It specifically targets and snips apart the polypropylene plastic, while leaving the polyethylene plastic completely untouched. The process itself is called hydrogenolysis. The mixed plastics are heated to a relatively low temperature, about 200 degrees Celsius, which saves a lot of energy. With the nickel catalyst and some hydrogen gas, the catalyst is incredibly efficient and selective. It finds the weaker chemical bonds in the polypropylene molecules and breaks them down. The result is that the solid polypropylene turns into a valuable liquid, like a lubricant or a wax. The solid polyethylene, meanwhile, is left behind, now pure and ready to be recycled into new plastic products. It is a brilliant way to sort two very similar materials. One of the coolest things about this method is that it is surprisingly tough. It can handle a lot of contamination. The researchers found that it even works when the plastic mixture contains up to 25% PVC, a type of plastic that usually wrecks recycling equipment. In fact, the PVC actually seems to make the catalyst work even better. The main challenge, however, is that this process does not create a fully closed loop for the polypropylene. It breaks it down into useful fuels and waxes, but not back into the building blocks to make new polypropylene plastic. Still, it turns a worthless waste product into something valuable, which is a huge win. Get ready for something straight out of science fiction. In South Korea, scientists at the Korea Institute of Machinery and Materials have developed a method that uses plasma, the fourth state of matter, an incredibly hot, electrically charged gas, to recycle plastic. If mechanical recycling is like sorting and melting, this is like using a lightsaber to vaporize the plastic back into its original atoms. They use a device called a hydrogen plasma torch, which can reach temperatures between 1000 and 2000 degrees Celsius. That is hotter than the inside of a volcano. This extreme heat breaks down plastic waste in less than a tenth of a second. The real genius of this plasma gasification process is what it can handle. You do not need to sort the plastics. You do not even need to clean them. You can throw in a mix of different plastic types, complete with their paper labels, leftover food bits, and all. The intense heat, combined with hydrogen and the absence of oxygen, instantly breaks down the long polymer chains of the plastic into their most basic chemical building blocks. It is the ultimate deconstruction machine. This could completely eliminate the most expensive and difficult steps of our current recycling system, sorting and washing. What comes out of this process is remarkably clean and simple. About 70 to 80% of the output is just two valuable molecules: ethylene and benzene. These are fundamental ingredients used to make brand new, virgin quality plastics. In fact, researchers say that over 99% of the gas produced can be purified and used as feedstock to create new PE, PET, and polystyrene plastics. This means we could finally achieve a true closed loop where old plastic bottles and containers can be broken down and reborn as brand new, high-quality products, over and over again, without any loss in quality. Of course, creating that much heat takes a lot of energy, and that is the main challenge for this technology. The energy costs could be very high, especially when scaling up to an industrial level. Another question is where the hydrogen comes from. Most hydrogen today is made from fossil fuels, which is not ideal. Using green hydrogen made with renewable energy would be better, but it is currently much more expensive. The Korean researchers believe that the profits from selling the valuable ethylene that is recovered could be enough to offset the system's high energy costs, potentially making it economically viable. A full-scale plant is planned for 2026 to test this out. Our next breakthrough takes a completely different approach. Instead of using powerful chemicals or extreme heat, this method harnesses the power of nature. A French company called Carbios has pioneered a process that uses enzymes, tiny proteins that living things use to speed up chemical reactions, to break down plastic. They found and engineered a special enzyme that essentially eats a specific type of plastic. It is a gentle biological solution to a tough industrial problem. It's kind of like recruiting a microscopic cleanup crew to do the hard work for us. This process, called enzymatic hydrolysis, works specifically on PET plastic, the material used for drink bottles and polyester clothing. The plastic waste is shredded and placed in a large vat of warm water, around 70 degrees Celsius. Then, the engineered enzymes are added. Over the course of about 10 hours, these enzymes get to work, using water to snip the long PET polymer chains back into their original pristine building blocks, terephthalic acid and ethylene glycol. The process is incredibly effective, breaking down over 90% of the PET into these core ingredients. Once the enzymes have done their job, the two chemical ingredients can be easily filtered out and purified. The beauty of this is that the resulting materials are identical to the virgin materials made from fossil fuels. They can be used to create brand new crystal-clear food-grade PET plastic with no loss of quality. This means a plastic bottle could be recycled back into an identical plastic bottle again and again, creating a perfect circular economy. The process is so effective that it can even handle materials that are impossible for mechanical recycling to deal with. For example, Carbios has shown that its enzymes can break down colored PET bottles, complex multi-layer food trays, and even old polyester clothing. They successfully took a pile of old, mixed-color polyester fabrics and turned them into a brand new, pure white t-shirt. This is a game-changer for the fashion industry, which creates enormous amounts of textile waste. Carbios is now scaling up, building its first commercial plant in France, which is set to begin recycling 50,000 tons of PET waste per year starting in 2025. This technology shows that sometimes the most elegant solutions come from biology. So, we have three amazing new technologies: a chemical catalyst from the USA, a high-heat plasma torch from South Korea, and a plastic-eating enzyme from France. Each one is a brilliant piece of science, but they all work in very different ways and have their own unique strengths and weaknesses. There is no single best solution that can solve the entire plastic problem on its own. It's like having a toolbox with three new, powerful tools. You would not use a hammer to turn a screw. You use the right tool for the right job. Let's compare them. The American chemical recycling method is fantastic for sorting mixed polyolefins like PE and PP, which make up the bulk of our plastic waste. Its big advantages are its low operating temperature, which saves energy, and its use of a cheap nickel catalyst. It can even handle contaminated waste. Its main limitation is that it breaks down PP into fuels and waxes, not into new plastic. So it is more of a high-value downcycling process. It turns waste into a resource, but it does not close the loop for polypropylene. The South Korean plasma gasification method is the most powerful and versatile. It is the powerhouse of the group. It can take any kind of unsorted, dirty plastic and obliterate it back into its basic chemical building blocks, creating a true closed-loop system for many plastic types. Its biggest hurdle is its massive energy consumption. The success of this technology will depend heavily on whether the value of the recovered materials can truly pay for the energy bill, and whether we can power it with clean energy to avoid creating a different environmental problem. The French enzymatic recycling method is the most specialized and elegant solution. It is a precision tool. It targets one specific type of plastic, PET, and uses a gentle, low-energy biological process to return it to a pristine, virgin-quality state. This is perfect for creating a circular economy for drink bottles and polyester textiles. Its main challenge is that it is currently limited to just PET and polyester. It cannot help with the millions of tons of other plastic types that are clogging up our landfills and oceans. Each technology, therefore, solves a different piece of the puzzle. After looking at these incredible breakthroughs, it becomes clear that the best path forward is not to pick one winner. Instead, the most effective strategy will be to use all of them together, along with our existing mechanical recycling systems. We can think of it as creating a multi-layered defense against plastic waste. Each method can be deployed where it makes the most sense, creating a smarter, more efficient, and more comprehensive recycling system for our entire planet. This kind of integrated approach allows us to play to the strengths of each technology. Imagine a future recycling facility. A truck full of mixed plastic waste arrives. First, the easy-to-recycle materials like clean PET bottles and HDPE milk jugs are pulled out and sent to a traditional mechanical recycling line. This is still the most energy-efficient method for these clean materials. Then, the remaining jumble of mixed polyolefins, like yogurt cups, and plastic films, is sent to a chemical recycling unit like the one developed in the USA. This process would separate the PE for recycling and convert the PP into valuable lubricants. What about the really tough stuff? The heavily contaminated multi-layer plastics and the polyester clothing mixed with other fibers. These unrecyclable items would no longer be sent to the landfill. The PET and polyester portion could be directed to an enzymatic recycling facility, like the one from France, to be reborn as new bottles and fabrics. The rest of the truly mixed and messy waste, which nothing else can handle, would go to a plasma gasification plant. There, it would be cleanly converted back into fundamental chemical feedstocks to create a whole new generation of plastics. This vision of a hybrid system is the most promising path to truly tackling the plastic crisis. No single technology is a silver bullet, but together, they form a powerful arsenal. Of course, technology alone is not enough. We also need smart policies from governments, like putting a tax on new, virgin plastic to make recycled materials more competitive. We need companies to design products that are easier to recycle from the start, and we, as consumers, need to continue to do our part. By combining new science with smart policies and collective action, we can build this better system. For a long time, the future of plastic has looked pretty bleak. We have been producing it at an alarming rate and have not had a good way to deal with the waste, leading to polluted oceans and overflowing landfills. The problem seemed too big, too complex, and too expensive to solve. But now, thanks to the tireless work of scientists and engineers around the world, the story is beginning to change. These new breakthroughs in chemical, plasma, and enzymatic recycling are more than just interesting experiments. They are beacons of hope. They show us that a future without plastic pollution is not just a dream, but a real possibility. These innovations are fundamentally changing what it means to recycle. We are moving beyond the simple, but limited model of mechanical downcycling and into an era of advanced recycling. We are learning how to unmake plastics, to break them down to their very core and build them back up again. Good as new. This creates the potential for a true circular economy, where the materials we use are not just used once and thrown away, but are kept in a continuous loop of use and renewal. This is how we can stop mining the earth for more oil and gas to make plastic, and instead, start mining the mountains of waste we have already created. The journey ahead will still be challenging. Scaling these technologies from the laboratory to a global industrial level will require massive investment, political will, and international cooperation. We will need to build new infrastructure, create new supply chains, and change the economic incentives that currently favor new plastic. It will not happen overnight. But, for the first time, we have a clear and scientifically backed roadmap for how to get there. We have the tools to sort, deconstruct, and remake plastic in ways we could only imagine a decade ago. The fight against plastic pollution is one of the defining challenges of our time. But it is a challenge we can meet. By embracing scientific innovation, working together, and rethinking our relationship with this incredibly useful but problematic material, we can clean up our planet. We can protect our ecosystems and our health. We can build a cleaner, safer, and more sustainable world for ourselves and for all the generations that will follow. The future is not something that just happens to us. It is something we build, and with science as our guide, we can build a future that is bright and finally clear of plastic.